All right, welcome back to linear algebra. We're gonna jump right into Anki. Come on now, bro. All right, 3 flashcards. What is the entry in row I and column J of the transpose of A if A equals basically lowercase ij? It's gonna be lowercase a sub ji. Flip them. What is the trace of a square matrix and how is it denoted? A trace is denoted lowercase tr, and then it's parentheses, and then the matrix is within the parentheses. A trace is the sum of the entries of the main diagonal. Okay. And then finally, what's the last one? What is the transpose of an MXN matrix A and how is it denoted? Transpose is going to be denoted the matrix to the power of capital T. It's basically the NXM matrix where the subsequent rows are basically switched into the subsequent columns and vice versa. That's good. What did we read about yesterday? What did we learn about in linear algebra? Well, identity matrices, zero matrices, and properties of matrix multiplication. So matrix multiplication is not commutative, though it can be, but it's generally not, so it's considered not to be. This means that A times B does not equal B times A. Cool. That's good. Zero matrices. These are matrices that in which all their entries are equal to 0. These matrices can be denoted by 0, and when they are so, they can be manipulated arithmetically. They operate very similarly to a normal 0. So the matrix A plus 0, given that it's defined, is equal to A, right? Just like in normal arithmetic. Given that it's defined, A times 0 is 0. The product is defined. If it's a scalar, C is 0, well then 0 times A is also 0. So then identity matrices. Identity matrices are known to be identity matrices. They're known to be called identity matrices, and not by accident, meaning that they're called that because when you have a matrix times an identity matrix, or an identity matrix times a matrix, given that the product is defined, which it is, because you shape the size of the identity matrix according to the first matrix. When you multiply a matrix times an inverse matrix, when you multiply a matrix times an identity matrix, you get the original matrix. When you multiply an identity matrix times a matrix, you get the original matrix again. So that's good. Yeah, they are square matrices. No, they're not. They are? Oh, wow. Okay. So identity matrices are square matrices. That's something that I just kind of learned. I wrote that down, but I forgot it. Okay. Right. So with these zero matrices, they don't follow all the properties typical of arithmetic. So this cancellation law in typical arithmetic is A times B equals A times C. If that's true and A doesn't equal 0, then B equals C. That's not typically true. That's not necessarily true for matrices. Just as the product of two matrices equaling 0 does not mean that one or the other or both of the matrices are 0. So typically in arithmetic, we say A times B equals 0, then either A or B has to be 0, at least one of them. Not true for matrices. You can have two non-zero matrices that give you a 0 product. All right. Anything else? No. Looks like we're good to keep moving. So I'm going to continue reading now, and then I'll be back to recall what I learned in a little bit. All right, guys, there's a lot to recall here. So identity matrices. These play an important role in the inverse matrices. So in typical arithmetic, an inverse is essentially to the power of -1, right? So A to the power of -1 is the inverse of A. If you multiply them together, you get 1. It's the multiplicative inverse, aka the reciprocal. So in matrix arithmetic, this is similar. There's a similar thing, but it's not exactly the same. We call it the inverse of a matrix, or the inverse as well. And so how do we define the inverse? So we're referring to square matrices of the same size. If A times B equals B times A, and they both of those equal the inverse, or no, not the inverse, the identity matrix, then we can say that B is the inverse of A, and vice versa. A is the inverse of B. And, okay, so we also say that A is invertible, B is invertible, aka they're non-singular. A matrix that is singular does not have an inverse. So a matrix that is invertible has exactly 1. Matrix that is invertible has exactly 1 inverse. Right. Okay. And this has to do with the identity matrix and the associative law of matrix multiplication. Essentially, if you multiply A and B together and it's the inverse, or it's the identity matrix, well then, if you times that by C, well then it's equal to C. And if you times B, C first, and you get I, no, you times A and C first, and you get I, then times that by B and it's B, so B equals C. That's essentially the overview of the proof. We can denote the inverse as similarly to typical arithmetic, so it's to the power of -1, so the matrix to the power of -1. Before we got into the inverse section, we actually, for the identity matrix, we had basically a proof and a theorem that if you got a square matrix, the square matrix in reduced row echelon form, it's either going to have at least one row of zeros, all zeros, or it's going to be an identity matrix. All right, and as far as the inverse of a matrix goes, it should not be thought that it's the matrix to the -1 should not be thought of as the matrix divided by 1, or the 1 divided by the matrix, like typical arithmetic. That should not it cannot be thought like that, because matrix division is not defined. Oh, all right, what are we missing? Got that. Got that. Got that. Got that. Got that. Got that. Did I say if you've got a square matrix and it has a row of zeros or a column of zeros, it's going to be singular every time. I don't know if I said that or not, but that's the case. An invertible matrix has exactly one inverse. Okay. Yeah. So we're going to continue with the inverse of a matrix tomorrow. Inverse properties of inverses tomorrow. This is actually in properties of inverses. So nowadays we get theorem and we get proof. Theorem, proof. There's so many proofs in this text now. Which takes a little bit more time to think through, but it's probably a good thing. Getting more advanced in mathematics. All right. Well, that's it for today. I will talk to you tomorrow. See you.